I'd like to invite Professor Robert Watson, Professor in System Security and Architecture at University of Cambridge. After Professor Watson's presentation, we will hear from Richard Grisenthwaite, Chief Architect and Fellow at ARM.
So I'll talk to you hopefully on the more brief side to give you a bit of background about CHERI, which is the technology underlying Morello's security extension. So this is extremely collaborative work, as you'll see from our long list of co-authors. I want to particularly acknowledge my co-investigators, Simon Moore, Peter Sewell, and Peter Neumann. So just to briefly introduce, CHERI is a new hardware technology. It's an extension to processor designs that is intended to mitigate software security vulnerabilities. Work on CHERI began at the University of Cambridge and SRI International in 2010, supported for about a decade by DARPA. We began a collaboration with ARM in roughly 2014, and supported by UKRI in 2019, ARM announced their Morello processor system on chip and board, which Richard will tell you about in a few moments. What I'd like to do today is talk to you about what CHERI is and a little bit about how it works, what kinds of software we're currently able to run on it. Certainly, we're not yet running all the software we'd like to, and we have high ambitions to run much more. But of course, a point of this research program is to help bring software ecosystems to the CHERI architecture, and then tell you a little bit about the kind of evaluations that have been run to date. And this is important because part of the Technology Access Program is asking for feedback and experimentation with the platform to help us understand how to improve it on the pathway to potential future products. So what is CHERI? CHERI is a processor architectural protection model. You'll notice throughout this talk, I'll use the term architecture. I'll be referring to the instruction set architecture of a processor. It composes an idea, something called a capability system model, with the hardware and software running on the computer system. And what we do is we add new security primitives to that instruction set architecture, new instructions that we can use and new data types. And then this is implemented by the microarchitecture or the hardware inside the processor and the broader chip. And this is going to, with any luck, enable new security behavior in software that runs on top. So what kind of new security behavior do we want? Well, the goal of CHERI, suggested by Matt, is to mitigate vulnerabilities in C and C++ trusted computing bases. These are the critical pieces of system software, language runtimes, hypervisors, web browsers, and so on, that actually are responsible for a vast bulk of the security vulnerabilities and exploitation that take place today. CHERI enables two kinds of new functionality. The first of these is fine-grained memory protection. The goal of this is to deterministically close to the greatest extent possible, vulnerabilities and also exploit techniques that are used and relate to memory safety in C and C++. The second aspect is scalable compartmentalization. This takes the idea of software sandboxing and allows us to substantially extend and enhance the way in which we compartmentalize software by breaking it into pieces that are isolated and protected from one another. What does this look like in the big picture? Well, as I said, we intervene, if you will, in the instruction set architecture, adding these new data types. In the microarchitecture, we implement new features, such as this capability data type. We introduce tagged memory, and these collectively serve to enforce a set of invariants, controlling the manipulation and use of capabilities on which we're going to build other kinds of software data structures and types, such as pointers. There are a set of rules for that use and those manipulation, rules like monotonicity, provenance, validity, and so on. They're going to prevent the injection of values and their improper manipulation. So we move up the software stack, software is going to configure and use those capabilities. Sometimes this will be done automatically as a result of compilation. Sometimes this will be done explicitly as a result of programmers describing what it is they want to protect and prevent. And we're going to get out of that sort of these low-level memory safety properties, but also higher-level constructs such as compartment isolation. Talk a little bit more about these two properties. So efficient fine-grained memory protection is intended to close vulnerabilities and prevent exploitation. These are similar and yet different concepts. The goal in the CHERI design was strong source code level compatibility. This means that programs have to be recompiled. There is a binary incompatibility that is comparable to the upgrade from 32-bit systems to 64-bit systems. Your 64-bit systems can run 32-bit code, your 32-bit systems can't, and there's an ecosystem update to bring the world towards 64-bit. And you can do an incremental deployment of 64-bit while still running your 32-bit software. CHERI's protection is deterministic and secret-free. These concepts are important. They distinguish the work in CHERI from many other mitigation techniques that exist today as they bring spatial and temporal memory safety. Secret-free is especially important because it's quite hard to keep secrets in the world of computer science. Leaked data values, the ability to attack more probabilistic protection mechanisms really weaken the fundamentals that are intended to protect the software stack from exploitation and arbitrary code execution. Thus far, a number of retrospective studies have looked at the impact of CHERI memory safety with any limitations it comes with and concluded that they would deterministic close roughly 2/3 of past memory safety vulnerabilities. I'll come back to that point in a few minutes. And that on the whole, in the early studies, the overheads of this are modest in terms of performance overhead, somewhere between 0% and 5% overhead, depending on the type of workload, but that there are workloads which experience higher overheads. And those are workloads we particularly want to explore and optimize as part of the research program. Second aspect, again, was the software compartmentalization. Here, CHERI supports a number of different, what we call software operational models. You can encapsulate objects inside your processes. You can improve the performance of process communication. The goal of software compartmentalization is to increase attacker workload. Attackers have to find and then exploit multiple vulnerabilities. We see this used in sandboxing today. Compartmentalization allows us to take this much further. The attacker workload is increased because in order to fully exploit the system, they have to perform many of these attacks. They have to grow the length of their exploit chain, and that is both a significant investment of work or financial investment. The claims we make today in terms of evaluation are that in early benchmarking on FPGA-based designs, we've seen as much as a 90% reduction in inter-process communication overhead, which means you can afford more compartments than you could afford in earlier designs. There are other things that you can do with CHERI, tend to be on the more researchy side currently, looking at the reinforcement of language runtimes, safe communication between different programming languages. These will also be important things we can do with CHERI, but they're not yet things we're encouraging the non-research community to do. They aren't yet well understood techniques. Probably can't get away without telling you a little bit about capabilities themselves. Capability extends the integer memory address used in the computer system to access memory. It adds additional metadata controlling how it can be used, and it adds tags protecting the integrity and the safe derivation. So when you modify the value of a capability in an improper way as a result of memory corruption or injection of the network, it is no longer possible to dereference the capability as the tag has been cleared. And again, just at a high level sketch, what is the impact on software? Well, your software is, both explicitly and implicitly a web of pointers and interconnections. Integer addresses allow you to access the globals, the heap, the stack, and so on, the memory execute code. Under the hood, they're also protecting implied pointers to implement access to globals or to implement the stack itself. What we're going to do when we use CHERI memory safety is substitute capabilities for integers throughout the compiled and linked code, which is going to reinforce the existing code structure with few, in some cases, if any, modifications at the source code level. The bounds and the permissions associated with the capabilities are going to be refined by various pieces of software in the system, from the kernel and the linker, compiler-generated code, the memory allocator, and so on. Most of these changes will be invisible to most programmers. And then the hardware is going to enforce these rules, requiring memory access to occur through capabilities and not in other ways. And the tags will ensure the integrity and the provenance validity of all pointers implemented in terms of capabilities. These capabilities, as I said, are refined by software, and we have a number of kinds of protections out of them. Referential memory safety is the protection of the pointers themselves from corruption. Spatial memory safety and privilege minimization allows us to restrain pointers so they can only access the intended memory. And temporal memory safety prevents use after free attacks or use after reallocation attacks from allowing confusion between different objects. It's a commonly used attack technique. These are applied automatically, both at the language level, so the kinds of pointers that programmers are working with daily in their data types, and also what we call the sub-language level. You might wonder, if you have strong language level protection, why do you need sub-language protection? Well, the answer is both that there are limitations to what CHERI can do, but also the programming languages themselves require a certain amount of type confusion in their current designs. And so we need to reinforce what falls underneath the programming language in order to protect against openings opened by the structure of the programming language. I won't talk very long about compartmentalization scalability, but I'll explain that CHERI is intended to dramatically improve that scalability. We want to have more compartments, we want to be able to change between them more quickly, and we want to be able to share memory between them much more quickly. And once we have these facilities in the hardware and the software stack, we're able to use them for a variety of purposes. One example might come to mind is if you have a mail reader or a web browser, they are convergence points between data from many different potentially malicious parties. And today we can use processes in computer systems to constrain them to some extent, but the constraints are very coarse-grained. We can isolate an entire tab of the browser or maybe access to a site, but we cannot afford to isolate the processing of every image. If one malicious image comes in via a mailbox, for example, the attacker should not gain access to all the other messages in the same mailbox. And this is the kind of thing we'd like to be able to do by deploying CHERI and using it in our software. Unlike memory protection, there is an implied change to software structure from using compartmentalization. The extent of that change is not well understood today. When we sandbox software today, the changes can be disruptive. They can require structural change, and other times they can flow very naturally. And so this is one of the topics we'd like to explore as part of the Morello research, is the impact on software structure and the potential expense in developing and maintaining those structures. Just talk a little bit about the software stack that will be available once you have access to the Morello board. There are in fact two software stacks. There's a software stack developed by the University of Cambridge and SRI, shared components with a software stack provided by ARM. The University of Cambridge and SRI stack is a complete open source software stack, compilers, operating systems, hypervisors, debuggers, and so on to demonstrate CHERI. They're intended to use CHERI extensively, but in an incrementally deployed way. They're intended not to fully and extensively disrupt the software stack. We want to keep around those properties that we like about current software designs. At the bottom of the stack, we have a Clang LLVM-based compiler suite. ARM has extended this to work with the Morello platform and not just with our CHERI research prototypes. Well, we will have, although we haven't yet released, an adaptation of the Google Hafnium hypervisor. We then have a FreeBSD-based operating system stack, CHERI BSD and Morello. This includes memory safety and compartmentalization features throughout its design. Memory safety in all user processes, as in the kernel, different mechanisms for compartmentalization, and also, in fact, as of a few days ago, support for Morello extended Beehive hypervisor, which allows us to host guest operating systems that themselves use capabilities. And on top of that is an open source application suite with applications from KDE and WebKit, Python, and so on. This is a growing corpus over time. Its size is limited today, but we've been able to demonstrate rich use up and down the stack. I'll leave it to Richard to discuss the software stack being provided by ARM that includes both Android and Linux adaptations. Talk very briefly about evaluation. One of the most interesting pieces of evaluation work was an independent evaluation performed by Microsoft Security Research Center, MSRC, who are both Microsoft's Red Team and also help and assist with evaluating new security technologies. The metric that they use to understand the effectiveness of technology is the extent to which it avoids the need for software updates, since software updates incur a high risk to customers in terms of impact for potential downtime and so on. They consider a vulnerability to be mitigated if no security update is required. It also, there is considerable engineering and QA effort that goes into the production of updates. It's quite a big deal if you're inside Microsoft, if you can substantially reduce the extent to which vulnerabilities are considered exploitable. They've written up a great blog post and a 42-page technical report looking at these topics in details, which I will leave to the reader. But the key point is that this deterministically mitigated at least 2/3 of those issues. And just a final case study I'll mention briefly. This was an Innovate or UKRI funded study at Capabilities Limited looking at adapting an open source software stack. We selected a significant slice of the software. We implemented memory safety and we whiteboarded compartmentalization. We then evaluated those changes by looking at lines of code modification and a 5-year retrospective vulnerability analysis. The full report is available online. The key outcomes were that we adapted 6 million lines of code in roughly 3 months, compiled for memory safety, did 3 compartmentalization case studies, and overall achieved a 0.026% line of code modification rate across the corpus, and a roughly 74% mitigation rate for all vulnerabilities using memory safety and compartmentalization. I will point you, just to conclude the talk, at our Introduction to CHERI technical report, which discusses the approach through architecture and microarchitecture in some detail. This report slightly predates Morello. We will have a new version of this report out soon that also covers Morello, but the concepts all apply quite well. So in conclusion, CHERI are these architectural primitives requiring some rich hardware and software evaluation. We're able to provide fine-grained memory protection for C and C++, compartmentalization techniques that are significantly higher performance than traditional MMU-based techniques, and also now an experimental implementation from ARM where we can evaluate some of these claims at a much larger scale and explore deployment issues. I'll point you at our website and a number of technical reports there, which will perhaps answer some of your questions and help you explore these topics in more detail. Thank you very much.
So following on from Robert's presentation, I'm now going to talk on behalf of ARM about our involvement in this program, which is under the code name of Morello, which we're making widely available through this technology access program. And I would say on behalf of ARM, we're very excited about this overall program. We want to thank UKRI for its creation of the Digital Security by Design program overall and the opportunities this is giving to explore this exciting technology. So just a reminder of what ARM is. ARM is the owner of the world's most widely deployed CPU architecture. We design process designs that we make available to many silicon partners. Most of the world's major silicon companies produce processors based around our technology. We have about 2,000 active licenses across the industry with 600 licensees, and around 2 billion of our processors have been shipped in a whole range of different markets, from obviously things like mobile phones, where the vast majority of mobile phones run on ARM technology, and also increasingly in things like networking, in servers. The world's largest supercomputer at the moment, Fugaku, is based on ARM technology. But it's not just the big systems, also many sensors and embedded processors in things like automotive systems and so on are based on ARM. We're seeing many billion devices actually being shipped each year now as a result of the wide use of our technology. And we're very excited to explore how to improve security, because security is a fundamental challenge for computing along the lines that Matt talked about. It's not a solved problem by any means. These vulnerabilities that can come from a simple typo have, they've been around, the concepts of them have been around forever, and they keep on coming, and the sheer number of things like memory safety issues that exist are a real concern. So with the Morello program, we're really looking to provide a platform to help people explore the CHERI technology that Robert was talking about a few minutes ago. Security vulnerabilities are a huge problem. CHERI has a lot of promise. The studies that Robert talked about with relatively small number of lines of code that need to be changed, addressing 70+% of the vulnerabilities in some of the case studies that have been looked at. Tremendous amount of promise, but also we need to do a lot of investigation about how this can be really used. Can we really, in industrial grade corpuses of software, get the benefits that the more limited studies seem to hint at? And particularly with things like the scalable compartmentalization, has been talked about throughout the session. We've got a big question about, if you are able to do much more compartmentalization than you can do today, what would you do with it? Is that really going to be a usable technology to put into people's hands? And really, what we're doing with Morello is putting out a highly capable system to allow people to explore what they would do given these technologies, to allow attackers to then say, can we find easy ways of breaking what we think are secured systems because they're using this technology? So again, we have to be sure that we don't just apply a sticking plaster to the problem, but that what we're putting out here has longevity. And the idea really about Morello is it's a prototype system to allow the experimentation that we need to get feedback from, to take this forward. And I keep stressing this prototype nature. What we put out there is it's actually bigger, it's got more functionality than we think would be deployed in a commercial system, because we want to try different ways of doing things and make choices between two different ways that the CHERI concepts could be used to be able to justify how to go forward. What does success look like if this program works out, and all of the work that all of the various partners that John talked about, and yourselves, if you access this technology through the Technology Access Program? What success really looks like is that people will find compelling uses of this technology in addressing security challenges, such that we're then able to really make the case that this should be a mainstream part of processor architecture. And I'm very clear here that we want that would be an enabler to see this in ARM's processors going forward, but we're not trying to monopolize this technology by any means. We'd be more than happy if this technology appears in x86 architecture systems, in RISC-V, in any of the processor architectures that exist, because actually that will mean that this is a technology that people can count on and be using wherever, and it just so happens that ARM's implementations have got it as well. And that's a very important part, that the fundamentals of the technology here are not being patented and any architecture is able to use it. This is not an attempt by ARM to monopolize this technology. So what have we produced? Some of the earlier talks have talked about this, and the website at the top there, arm.com/Morello, has links to all of this material. We have this prototype architecture. We have a software model of the Morello platform. We've got a form of the operating system out there. We've got tool chains. We've got a partner forum, an FAQ to allow people to interact with it, technical reference manual for the board, as well as this test chip and board that is now just about reaching the point in which we're making it available to the many participants in the Digital Security by Design program. What is on this board? The basic principle behind it is a highly capable board, capable to be used for both client and server type systems. So this is slightly unusual as much as we haven't targeted any particular market. We built prototype processors with this new instruction set architecture in it that are actually based on the processor cores, the Neoverse N1 cores that we have shipping and used in things like the Amazon Graviton G2 processors. They don't have this technology, but we took that as the starting point, and these are highly capable out-of-order processors. We put 4 of these down and enhanced it with this Morello capability, or adding in all of the CHERI technology that Robert has talked about before. And then as part of that, put that throughout the system. The board is being provided with 16 gigabytes of memory that's expandable up to 32 gigabytes. It's got a PCI interface. It's fully compliant with the SBSA, which is a standard that we've been progressing in order to make it much easier to run software out of the box on these sort of systems. Just a couple of pictures of the demonstrator board. If we were live, we'd be actually showing you this running, but we have to make do with some pictures. It's all very well having hardware available, but hardware on its own isn't really what we need. We need hardware and software. And as Robert talked about, Cambridge has done a tremendously good job of doing a port of FreeBSD to make full use of capabilities throughout its technology. But we're also providing a whole bunch of software work streams as part of this program. And at this point, we've got things like Linux up and running. We've got full development environments and tool chains there as well. And we'll be continuing to update that. We started releasing this software in October 2020 to work on our software model that anyone can go and download. And now we've got the SoC up and running in people's hands. We're going to be expanding to bring in more of the application of Morello into the Linux kernel, and specifically supporting and enforcing capabilities at the kernel user boundary, and developing a GCC-based toolchain in addition to the initial LLVM-based toolchain. The range of software available, Robert talked about how we've got that very much capability focused CHERI BSD. We've also got Android and Linux ported to this platform. UEFI and ARM's trusted firmware also all runs on it. So this is a really very capable board, capable system. It's got a decent graphics processor, so you're able to run graphics-oriented workloads as well as text-oriented ones. It can, as I say, be very much used for both servers and for server type applications and for client type applications, and the range of different partners really show that we believe this board can be used in many different places. And what we're really looking for from this is having put forward this open, this initial software for people to make use on, is that many of our partners will be collaborating and porting more software and making it available for this platform to allow us to essentially bootstrap around this new technology. And really the question is, with doing this, what feedback are we looking to get? Really, we need to understand the performance questions around a wide range of different usage models, because it's all very well putting out these different usage models, but this is a foundational technology, and we need to understand which ones are going to be performant, which ones aren't, allow us to refine the superset architecture that we've created, and from that, make decisions about which features really make sense for a commercially deployed architecture. We need to have compelling examples of why capabilities are useful. I've talked quite a lot, and Robert talked a lot about the scalable compartmentalization. How will people really use this to improve their security? Does that really provide the benefits that we think on paper that it should? Have we got some people actually faced with software that's been ported to these sort of platforms? Can they actually find ways of breaking the compartmentalization that has been created, and actually work around all of the benefits that we're claiming about? So we need to have some red teams going after us. We need to understand how the different languages and runtimes can really make use of capabilities. Matt talked a lot about C and C++, but we've got a lot more languages that run on top of this, JavaScript, Java, Rust, and so on. We need to understand better how the compartmentalization can be used. We need to understand the performance questions. And if this all works out the way that we think it will, this becomes a showcase to encourage other architectures to adopt capabilities, because really making use of that fine-grained compartmentalization, you want to be able to use that on any platform you're running on. So as I say, we're very keen to see this technology, assuming that it provides the benefits that we think it will, being used actually by many architectures. We've gained experiences of building an SoC around this processor architecture. It does have tentacles that go out into an awful lot of the system. We've made quite a lot of that available for other people to make use of, because the whole thing has been a learning experience. And by having that experience published, again, we are helping take forward this technology so that it can be widely used around the world. And at the end of the day, what we're hoping we get out of this is an architectural approach with formally proven security properties. Part of the work that's lying behind this program is a bunch of formal methods and formal proofs of the security properties going on. And from this, we will learn what to put into the future ARM architecture to give the digital security by design going forward. So the next steps, really, this is an opportunity for you to experiment with a Morello board. The technology access program that this event is all about is about giving you access, or getting you access to these boards if you wanted. We invite you to engage and contribute and be part of this program going forward, and just to help us understand whether this technology is worth genuinely deploying. We think it is, but this really is, you think about it, almost an advanced beta test of this concept to see that this is really worth putting out into the world's architectures. And Katie will be talking about how you'll be able to get access later in this session.
Thank you very much, Richard. I'd like to now invite Professor Watson back on camera, and to invite George Papadakis, Senior Innovation Lead at Digital Security by Design from CHERI, to a short Q&A session before we start with the panel.
Thank you, Dana. We already have some questions that have come in. Some of those have been answered, but those that we can answer. So let's have this one now from Ian Crawford. He's asking, can CHERI be retrofitted to existing software systems, or does it need to be included only in new implementations? I guess that's a question for Robert, most likely.
Yes, certainly give it a cut. Maybe Rich will have some opinions too. And certainly our experience with this idea has expanded as a result of the collaboration with Arm and their customers. In general, CHERI is intended to be incrementally adoptable in software. So yes, you have to have a chip that implements it. Once the chip is present, then you have some choices about how you deploy CHERI, both in terms of how you use it and in what software you use it. We have generally recommended an incremental deployment strategy that consists of introducing operating system support early. When you introduce operating system support, there are then different paths you can take depending on what you want software to run. As with the 32-bit, 64-bit transition, I think it is reasonable to assume that non-CHERI-aware software will run for the foreseeable future. That software will not get the benefits of CHERI, your existing program binaries, but also it can exist within an ecosystem, in some sense be protected from the world by the CHERI extensions elsewhere. On the memory safety side, essentially we have a new variant of C and C++. It is very similar to current C and C++, hence the 0.026 lines of code change for a very large software corpus, but it does require these modest changes. Those modest changes are generally hygiene changes. There are changes that will be acceptable in most cases to upstream source code repositories, vendors, open source communities, and we have upstreamed many of those changes. To perform software compartmentalization is a more disruptive change. Those sorts of changes do exist in some software already. If you look at, for example, the mobile phone vendors' operating systems, they often use sandboxing fairly heavily within web browsers, sometimes for plugins and so on. Those were disruptive changes on current architectures. That's not less true in CHERI. One of the challenges there is that maintaining both compartmentalized and uncompartmentalized versions of the same software could be more costly. We don't really understand that cost yet, but if it imposes structural changes, some of them will work on both, but testing and evaluation and so on is something you need to think carefully about. Obviously, we view a future world in which you're gradually moving towards extensive CHERI use, yet to be seen if that will be fulfilled. But we've worked very hard to provide a rich software ecosystem with debuggers and tracing tools and so on to help with that process. Happy to talk with people offline if they have questions about our experiences.
Thank you, Robert. There's another question from John Dalman. He's asking, Richard, how much does the Morello board cost?
Well, we're not actually making this a commercially available board. As I talked about a little bit before, this is a prototype architecture, and actually we're not providing backwards compatibility to this architecture. This is very much a prototype to allow people to experiment, and so we don't want it to be incredibly widely available. We want people to be able to participate. So the way this program's been put together through the Digital Security by Design and through what's going on being talked about as part of this Digital Catapult event is that we're providing access to the technology for people to be able to participate with the boards rather than making them widely available as a commercial offering. What that then allows us to do is actually have a bit of a partnership with the people who are using the boards to understand what's going on, and then once we get all the feedback and we say this is a great technology going forward, it will become part of a mainstream technology from ARM, at which point it will become commercially available.
That's great. Thank you, Richard. And last question, Robert, you did cover the retrofitting aspects. Christopher Williams is asking a question. In addition to the retrofit, he's asking whether changes in the C and C++ standards are needed to take full advantage of CHERI, basically.
It's an interesting question. I mean, we've tried to work wherever possible within the existing standards. I mean, one way to think about what we've done is that we've taken undefined or implementation defined parts of C and C++ and defined some new behaviors such as trapping when a buffer is overflowed. But we do require some changes in how pointers are used. The syntax language remains the same, but for example, you can't fit a full pointer inside your regular sized integer anymore. You have to use int pointer t, and this sometimes causes some source code change. We have a CHERI C and C++ programmer's guide available on our website, which I think does a pretty good job of exploring these issues. We plan to do an updated version of that later this year based on new experience gained. We've also done some work around, for example, compiler-based static checking to look for potential issues. About half the issues we find importing source code to CHERI are picked up at compile time by the compiler, but then there's a set of dynamic issues that can arise around memory alignment or pointer misuse. These tend to be picked up by various sanitizers or through dynamic testing. This is a topic happy to talk to people about in more detail if they find that useful.
Yep.
If I could just come in a little bit on that. One of the things we've learned from this overall program is that people don't really follow the rules of C. There's really quite a lot of de facto programming in C, and actually the way CHERI's been designed is to fit in with that de facto usage rather than the letter of the law as much as is possible. And there's been some really great papers which are on Robert's on the Cambridge University site that Robert talked about that actually talk about, you know, what is the de facto expectations of C, not just what the letter of the language says, because it is quite astonishing what we've learned from all of that.
Thank you both. Final question from right. There are more questions coming in, but I'll have to draw the line here. So I'll pick one from Tommy P. Christopher has already asked one. Has there been any research on how much modification or effort is needed to get Java or JavaScript working with capabilities?
Yeah, maybe I could take this one as well. To some extent, with respect to JavaScript, we have the WebKit JSC JavaScript core runtime up and running on Morello, including a just-in-time compiler. This was collaborative work with ARM. It works very well. We don't have, in terms of functionality, we think improved security as a result of the resilience. We're looking to do a structured evaluation of security change and also performance impact over the next 6 months, and can hopefully report back more on that. There is an OpenJDK adaptation taking place as part of the University of Manchester, Manchester University contribution to the CHERI project, which is an Innovate funded project. Probably too soon to talk about results from them, I expect, but I think this is one of the questions we really hope to engage with in the first year of this program is what happens with these managed language runtimes? How do they perform? How easy is it to adapt them? And do we gain security benefit for them as well? I think we have good reason to think we would, since vulnerabilities in language runtimes are quite a big thing currently. Often the language runtimes are written in C and C++. They suffer from all these exciting problems, but much is to be learned there still.
And just to be slightly clear there, that's essentially modifications to get the runtimes running. You're not going to have to change your Java or your JavaScript programs at all to make use of this. This is absolutely underneath the hood. It's below the language level stuff.
Thank you very much, both. I'd like to bring this Q&A to an end. Thank you all.